Well, thank you for the introduction. Good morning, everyone. So yeah, my talk will be about joint project with Pavel and about Euler characteristic curves and profiles. So this is the outline of my talk. I'm going to give you a brief recap of the main idea of TDA and what's persistent homology. Then I'm going to introduce you the concept of Euler characteristic curve and discuss their stability. Then we're going to go a bit into the multi-parameter persistent length and see how these Euler characteristic curves generalize to profiles. Then we'll briefly discuss some efficient algorithms to compute these things because math is cool, but you actually need to compute to do some data analysis. Then at the end, we'll discuss some application and experiment. So we have a lot of ground to cover, but thankfully we had a bunch of great talks already about TDA and persistent homology, so we'll just go very fast at the beginning, but feel free to interrupt me at any time if you have any questions. So yeah, topological data analysis. Yes, at this point we all know that the main aim of TDA is to extract topological features from our data, but yeah, the question is how do we do that? So the main tool that we have is an absolute simplicial complex that in the most generic definition is just a finite collection of sets such that each subset of a set is itself in the collection. Or if you want a more geometric definition, it's a collection of sets which is closed under the operation in spaces. So for example, here you have a very simple absolute simplicial complex and it's geometric realization, and you can describe it in a combinatorial way. Great. The other tool that we have is that we need to have filtration on top of our complex, which is a monotonic non-decreasing function over the synthesis, such that the filtration value of a phase is less or equal than the filtration value of its co-phases. And if we have these settings, then moreover you can easily realize that each sublevel set of this filtration complex is indeed a subcomplex. And this gives rise to a nested family of subcomplexes that you start from the empty set and then you go all the way up to your full complex. And that's great because if we have this nested family of complexes, then for each dimension D, we have a sequence of homology groups. So we can basically compute the homology at each filtration step. And then the homomorphisms between the homology group are just induced from the inclusion maps of your subcomplexes. And that's basically the idea behind persistent homology, because we define the persistent homology groups as the images of these homomorphisms. And in particular, we're going to refer as the ranks of this group as the persistent Bethe numbers. So intuitively, what these persistent Bethe numbers capture is how many homology classes that you have at one step in your filtration are still present at future steps in your filtrations. And we already saw this beautiful picture over here, and I said, that's why you should really focus on creating nice visualization, because then lots of people will steal them. And that's basically the idea, right? So we represent this persistent homology using barcodes or diagrams. Here we have barcodes of different dimensions. And so for each filtration step over here, you can see that, for example, here we have 3 one-dimensional poles. And so at this point, we have 1, 2, 3 green bars. So that's basically the idea what we can compute and the type of descriptor that we have. That's great. So persistent homology has been around for 15, 20 years. It's been a very successful tool in TDA and has a plethora of different applications in material science, biology, and cosmology also, which is very dear, very close to my heart. But what's the catch? Well, it's kind of hard to compute and prone to exponential expansion. So basically, the way you compute it is a version of the classic matrix regression algorithm. So that's basically takes time n to the power 3 when n is the number of syntheses that you have, and the number of simplices usually grows exponentially with the number of points. So that's kind of tricky. So can we use any other topological invariants that maybe are easier to compute to extract knowledge of our data? And so if you start thinking about, okay, what's the easiest topological invariant? Well, an answer is probably the Euler characteristic. So the Euler characteristic is probably the oldest and most famous topological invariant that was introduced by Euler and to describe polyhedra. So in its simplest formulation is just the alternating sum of the number of vertices, edges, and faces in a polyhedra. And then if instead of polyhedra you generalize it to simplified complexes, well, you just carry out this alternating sum over all possible dimensions. So the Euler characteristic of a simplified complex is just the alternating sum of the number of simplices of a given dimension. And then there is a nice result, very famous result in topology, that is the Euler-Poincaré formula, that the Euler characteristic of a simplified complex is also the alternating sum of its Betti numbers. And so here you can see the parallel with persistent homology, because we are interested in computing these Betti numbers, but those Betti numbers are kind of difficult to compute. But if you're only interested in their alternating sum, well, you can just compute the Euler characteristic, and instead of doing this computation, you just count how many simplices you have. So you turn a difficult problem into just a counting problem. So we will see that later on during when I will discuss the algorithms. But so that's the idea. So when you put persistence into that thing, you arrive at the definition of the Euler characteristic curve. So you start with a filtered simplified complex with a filtration function that assigns a real number to each simplex, and then you define the Euler characteristic curve as a function that assigns the Euler characteristic of each subcomplex defined as sublevel set at some filtration level T. So the Euler characteristic of K at filtration value T is just the Euler characteristic of the subcomplex KT. And that's great. So you can compute it, and for example, fancy animation always, capture attention. So here you have the Euler characteristic curve, which is a piecewise constant function that has values of the integer, because the Euler characteristic is always an integer. And you can see how this complex is growing. Over here, you're basically just capturing the number of connected components, because you have 7 points, and then the Euler characteristic goes down. Here, the Euler characteristic is 0 for quite a long time, while you see the central pole over here, and then at some point everything becomes connected, so the Euler characteristic stabilizes to 1, and it's 1 from here to infinity. Okay, so we can do that, and moreover, we can also, since these are just piecewise constant functions, we can define distances between them, because that's another important thing in TDA. You want to have topological descriptors of your data, but you also want to have ways of computing distances between them. So you can, you have your features, you can compute distances between your features, you can have your distance matrix or whatever, and then you can run whatever classifier or machine learning algorithm you want. And so there is a very natural, intuitive notion of distances between two Euler characteristic curves. You just take their one norm. And why you want to take a one norm instead of, I don't know, the two norm, just because these are piecewise constant, so it makes sense to compute the one norm. And so basically the difference between two Euler characteristic curve is basically the area, this gray shaded area over here. And that's nice, because now that we have measure to compute distances, then we can ask ourselves, okay, so if I compute the Euler characteristic of a complex, and then maybe I just wiggle the vertices or the filtration value of my complex around a bit, how much will the Euler characteristic change? Because if I'm interested in using the Euler characteristic as a topological descriptor, I will like to have some sort of stability results. And for a long time in in the community, there were some claims that this thing is not stable. You just modify your complex a little bit and this thing blows up, so you don't have any stability. But actually, if you go in the literature a bit and you pay close attention to some details, well, you can actually arrive at a stability result. So I don't have a lot of time to tell you what the Wasserstein distance between two persistent diagram is, but if you trust me, well, this side of the equation is very well studied and well known in the literature. So it's one of the most important theorems in persistent homology that if you have two persistent diagrams that describe two topological spaces, well, you can bound the Wasserstein distance between them. And the Wasserstein distance is basically a distance that comes from optimal transport problems. So this side is very well studied, so you can also bound this thing with other distances like the Hausdorff differences between your vertices and stuff like that. And so the fact that we can bound the distances between the Euler characteristic of our complex with this very well-known quantity is actually a very acute result. And moreover, maybe you already realize that, well, the Euler characteristic curve is just the alternating sum of the vector curves that Nicholas was talking about. And actually, the way you prove these results is that first you prove that this thing holds for vector curves, and then you just triangular inequality, and you have this result for the Euler characteristic curve. So this neat result is actually should convince you that you could use these things to do data analysis because this is stable enough. Okay, so that was some theoretical introduction. Now the fun part. So probably this is a new concept in this couple of days. What if we go into the multi-parameter persistence setting? So the main idea and multi-parameter persistence is that you have your filter complex, where you assign a real number to each simplex, or basically your you can say that you have an ordering of your simplices, right? So your simplices are indexed by a total order set, maybe reals or whatever. So what if you generalize it to just generic poset? So for example, here you have another nice picture that I always steal from the original Carlson and Zamorodian paper. What if you consider a family of complexes that are not indexed by just the radius or the conductivity radius, but also by the curvature here. So here you have a two-parameter families of nested complexes, and you're interested in just look at what happens over here. So I don't have time to go into details, but when you go to multi-parameter, posets, are more complicated object in general than just order sets, and so funky stuff, I think. But I'm happy to take questions if you're interested. Okay, so can we generalize the concept of the Euler characteristic curve to just these more general settings? Yes, we do. And so first of all, to tell you what poset index filtration is, so which is basically the thing that I just said. You take a subcomplex, you take a poset, and you just have the same condition for that we had before. Then you never you have x, which is lesser or equal than y in the poset, then the subcomplex ax is included in the set complex ay. And moreover, if you just you can have, well, this is a naming convention, but if you just your poset is just a product of a bunch of totally ordered set, you call it a multi-parameter or an n-parameter filtration. So that's just normal. And basically, you can have the same definition as before, but now we call this the Euler characteristic profile because it's no longer a curve. And of a field complex is just a function that assigns to each value also the Euler characteristic of the corresponding subcomplex. And so once again, you can imagine that, for example, in this case, here your positives are true. Here your Euler characteristic profile is a function that goes from R2 to the integers. So at each point here for curvature and radius, I'm giving you the Euler characteristic of this thing. So that's why we call the profiles. In 2D, some authors call it like an Euler characteristic surface, but nothing tells you that you have to stop at 2D. So in general, we call it a profile. And as I was warning you before, if you're wondering why this thing might help you, well, this is another standard example in TDA, which is, usually we all start with point sample from a circle, and you can, do persistent knowledge and say, oh, we detect a hole over here. But if I just place a single point in the circle, well, I will break basically everything. And why is that? Because if I try to compute the Euler characteristic of these two things, well, for the clean circle, I have a very long bar here at 0, which signifies that I have my hole here, because the Euler characteristic of a circle is 0. But if I have my single point in the middle, here you don't see the circle anymore, because everything becomes connected, and so the Euler characteristic is at 1. Here you have some wiggly, but this is very rapidly disappearing. So what can you do to remedy this thing? Well, maybe instead of just doing it for this radius parameter, you can also add another dimension that measures the density or the codensity. Say codensity because I want to include points in very dense regions first. And if you do that, you compute the Euler characteristic profile, you get these things. So this is for the clean circle, and this blue thing means that you have 0 Euler characteristic here. And also here, for the noisy circle, if here is the codensity value of the isolated point in the middle, but you can see that if you don't include this one, you still can see that there is a very big region in which you detect Euler characteristic is 0, which is the signal. Yeah.
What's your codensity function here?
Oh, you take something one over the radius is probably this. Is one of those ones that is on
so distance to spontaneous.
Yes, exactly. And then you have some sign in this sense. Okay, and so this should give you an idea of why sometimes you want to do that. And I was mentioning before, well, multi-parameter persistence makes stuff more complicated. So in general, is more difficult to discuss the stability of this stuff because, for example, if you just have a very simple two-dimensional profile and then you move it on the right by an epsilon, well, this thing here is not bounded, so their difference, which is the red part, will not be bounded because here this thing goes up to infinity, and this thing does not have any quantity because at some point everything stabilizes to 1. But if you think about real-world application, well, in general, you don't go up to infinity because your data is finite. So if you just truncate this thing up to value at infinity, well, then you can still have control on these type of differences over here. But this is a bit technical, so I'm happy to discuss it later. Okay, let's switch to algorithms because we want to compute stuff in an efficient way. And the main idea is that usually when you're starting from points, you use the Dioscuri complex construction that Nicolas mentioned already. So basically you connect points that are closer than a certain threshold, and then you let this threshold go at infinity. But the main idea here is that your the Dioscuri complex is a paired complex, so it's completely determined by its one skeleton graph because all the triangles are filled in. So you can basically reduce the problem of counting how many simplices you have here to just counting the clicks in your graph. And so that's basically the idea behind our algorithm, because in a complex theory, each simplex contribution to the Euler characteristic will be plus or minus 1 depending on its dimension. And this contribution will appear at simplex filtration level. And so the idea is that if we are able to obtain another list of all the simplices in our vectoristic complex, each one with its filtration value, then we can reconstruct the Euler characteristic curve by just summing up all this contribution. And this is what we do. And the trick that you do is just to exploit this simplex data structure that here you have like all your simplices of a given dimension in a tree. And so you just need to traverse this tree and keep track of each simplex contribution. And moreover, if you notice, all of these trees are independent of each other. So you can traverse this tree in parallel. So if you can go, you can have like one worker that does this tree, one worker that does this tree, and this one. So it's also embarrassingly parallelizable. And this is actually worse in the sense that you can see how the runtime goes down according to how many cores you're using. And at some point it's stabilized, because if you have a full complex, you can see that this tree is way larger than the other ones. So this is the worst case scenario, but in general, you can use some optimization tricks to just even out the size of these trees. Okay, but we also want to compute curves for image data. And so for image data, we saw yesterday that you don't use Vittori's Gibbs complex, we use cubical complexes. So this is another image that is stolen from that. And in this case, the construction is different. You start from an each domain, which is just a matrix of pixel values, and then you put them into your cubical complex. And then, once again, we want to compute the contribution of each one of these cells. And you can do it in a streaming fashion. So maybe I can first show you these things. So if you have a cubical complex, this one here, you don't need to load all the complex into memory all at once, but you can just have a chunk of them two. And then for this complex over here, you compute the contribution of this thing over here, and then you slide on the right a bit and you compute this thing. So also this thing you can do it in parallel because you take different chunks and you do it in a streaming fashion. So that's quite efficient. And if you want to see another fancy animation, yeah, that's all characteristic for two-dimensional image. And here you can see that it just, you have the number of magnetic components, it grows, and then as these black points start merging into each other, your energy goes down, and here you have a cycle for a brief moment of time. So that's the type of thing we can extract and we can efficiently compute. And now I can discuss briefly the experiment. I guess, okay. So some real data. So this is one of the most famous paper in multi-parameter persistence that actually show that you can have some results on real data. So the idea here is you have histological slices of tumors. So this is just a photograph of some tissue. And you're interested to see, so you take different regions over here, and you're interested to see how different immune cells, don't ask me what this thing means, I know that there are different types of immune cells. You want to classify these different things, and there are some biological reasons that tell you that different immune cells have different spatial patterns. So you have these photographs, you have like some experts that tell you, okay, at different point cloud that corresponds to different type of immune cells. And you want to see whether you can classify these different type of point clouds according to the different to their spatial pattern. And so that's what they did over here. And they used multi-parameter version of persistent landscapes that were introduced yesterday. So we exactly the same thing. So we took these points out, but instead of computing these multi-parameter persistent landscape, evaluate why is multi-parameter because they're using actually both the radius and the codensity. So that's why I had that very easy codensity example earlier. So we did that the same thing, but instead of computing persistent landscape, we computed two-dimensional Euler characteristic profiles, and then we just run an LDA classifier. And so then we compare our results to them, and well, the gray, this is our accuracy, and the green means that we are performing better. So I don't want you to see. So you have a different bunch of different classification tests for a bunch of different tumors, a bunch of different classifier, LDA, QDA, and stuff, and we are performing significantly better than the landscape. So that's the first idea. I don't think I have time to go into I have a fun example for just RGB images, but I'm happy to discuss about it later. But let me just stay on the real world application. So I will skip this. So that was an example for point cloud type data. What about image type data? So I'll stay on the medical application side of things, and once again with histological slices. So these are histological slices of prostate cancer. And in general, what the medical professionals do is they look at these slices and they try to classify them according to some, expert knowledge. So you have that these words describe the topology of the tissue, and according to apparently this is very bad. So grade 5 in this vision scale means that the tumor is very bad, and the grade 3 is that it's still a tumor, but it's a bit better. So what we can do, we take these images, and so this is an RGB image, but maybe you want to grayscale it and compute the Euler characteristic. But if you ever grayscale an image, it's like, how do you grayscale it? It's now extremely obvious how to do that. And moreover, these are Asian slices. So the color channels you're interested in are not the RGB ones, but you actually want to distinguish between these red things and these dark purple things, because apparently they stay in different type of cells and structure in the tissue, so that's actually the signal you want to extract. So the thing you could do is you could extract these two different color channels that I will not even try to pronounce this thing, but you can see that they actually extract different features. And here you are extracting the information about the cell nuclei, and here you're extracting information about the membrane. And so instead of doing Euler characteristic curve, you can do an Euler characteristic profile while you're using these two color channels as your two parameters, your filtration. And you get these kind of profiles of vector. So this is why if you increase these color channels, increase this color channel, and the color scale is using the Euler characteristic here. And does this thing work? Well, apparently yes, because if you are trying to classify between lesion 3 and lesion 4 cancer, the two-dimensional Euler characteristic profile performs way better than just doing what usually people do. They just focus only on the this color channel over here. So that's that's saying that you can actually gather some information by just going two parameters in this case separately. So I will end here. I'm more than happy to discuss any other topic that I have to just go through very fast. But just as remarks, well, ECCs are topological descriptors that can be applied to a bunch of different data sets, image point cloud, and also just working time series and stuff. They are easy to compute and machine learning friendly. We have our public code to do that. And moreover, they can be extended to the multi-parameter persistence in quite a general way. So we have our code, we have a preprint on the archive, and I will stop here on behalf of me and Igor. Thank you very much for your attention.